Welcome to the lecture series on image recognition with neural networks. This is lecture 5, gradient descent and backpropagation. The learning objectives are, we'll talk about the gradient descent algorithm, the chain rule visually so that we can know how to get the backpropagation formula and how to use them. Then we'll talk about the 4 equations of backpropagation, and we'll talk about mini-batch gradient descent. Gradient descent. Gradient descent is an iterative algorithm that gradually adjusts the parameters W and B to better reflect the training data by reducing the cost function. So here's the algorithm. We're trying to find the best parameters W and B, but initially we don't know what they are, so we're going to randomize them, and then we'll use those randomized parameters W and B, and we'll compute the gradient at that location. And of course, because the W and B are randomized, initially the cost function is very high because the model is a random model, and so we'll compute the gradient dJdW and dJdB. Remember, in the last lecture we talked about what it means to take the derivative with respect to a matrix. And so this is the gradient which points in the direction of biggest cost increase. So we're going to update the parameters. We're going to take a step in the direction of the gradient by going in the opposite direction. So here's our update rule. We take the old W value, which is the randomized value initially, and we go in the negative direction. This is why this is a negative. We take the negative of the gradient and multiply by a step size called alpha. So again, this is the old value of W. We'll go in the negative direction of the gradient, and this is the step size. And similarly, take the old value of B. We'll go in the negative direction of the gradient with this step size. So the step size is actually a hyperparameter. It's also known as the learning rate. And if the step size is too big, then our steps might be too. We might overshoot again, we're trying to find the minimum of this cost function, and taking a step size that is too big, we might overshoot it, and we'll keep overshooting back and forth, and we might not get to the minimum. If the step size is too small, then maybe the gradient descent is progressing too slowly, and we're learning too slowly. So you have to do some fine-tuning to get the right learning rate so that we can get to the minimum without overshooting and still do so efficiently. And then we repeat with the new parameters W and B. In other words, we'll compute the gradient again at the new location. We'll find the direction of the maximum decrease. We'll take another step in that direction, and then we'll repeat this. And every time we take a step, our cost function should go down, and the gradient is the direction to help us reduce the cost the quickest. So that's the gradient descent algorithm. It's kind of amazing that geometrically this is very simple. This is the analogy here is that if we were stuck on the mountain and we're surrounded by fog, we want to get down to the valley. One way of doing this is to kind of feel in front of, put forth our feet and kind of feel in front of us and find the direction of the biggest decrease, and take a step in that direction, and we'll keep repeating this. So certainly this algorithm has a nice analogy in trying to go down from a mountain. So here's an example to kind of make that very clear. Suppose that, let's take the step size to be 0.5, say half a step. Suppose that initially W and B is negative 0.9 and 0.1. So initially, again, this is W and B is on the domain space, which is, say, on the floor of this function. So here's the randomized W and B. And because this is randomized, initially the cost function is very high. So we see that by looking at the cost function, which is this point right here. And so we want to find the gradient. So here's a gradient, find the derivative. So negative 1.4 and 1.6. So negative means that we're going to go left. Positive is going right. If these are single variable, that's how we interpret it. So that means that here's a gradient direction. And if we take a step in that direction, we update by taking the O value W and minus multiple of the gradient. So here's the O value W minus the step size times the gradient, and we get this new value. And we do the same thing for B, take the O value of B, and we'll go in the negative direction of the gradient. And so that means that initially we might be over here. When we take a step, then taking that step allows us to reduce the cost function, reduce the error. And then we repeat this with, once we get to this point, the gradient might be different. It might be in a different direction. Every time we make a step, the gradient function might change. And so we take another step, and we reduce the cost function again. We keep repeating this until we get down to the bottom of the valley, which means that our cost function is minimized. We found the best parameters that can represent and classify our images. Here's the chain rule. The chain rule is necessary so that we can get the equations for the gradient. Okay, so if you've taken calculus, AP, or just calculus, you've seen the chain rule, which says that to differentiate, to find the derivative of a chain of function, f and g. This is a composition of f and g. So f is the inside function, g is the outside function. To differentiate this chain, we first differentiate the outside function. We differentiate in terms of the inside function, and then we multiply that by the derivative of the inside function. So here's a visual way to understand the chain rule. Again, this is by using the computational graph that we talked about in lecture 2. So here's x. We first apply f of x. This is the inside function, and we call that u as the intermediate variable. And then we apply g to u. So this is the composition of f and g. The chain rule says that to differentiate g, which is the last function, in terms of the first variable, we first have to go differentiate g in terms of the intermediate variable. So dg, du. And then we differentiate u in terms of the x variable. And then we multiply that chain. And so this makes sense because if I were to differentiate g in terms of x, that might be too complicated. But if I were to break that problem down into two smaller problems, differentiate g in terms of u, this would be a little bit simpler, and then multiply that by the derivative of u in terms of x. Again, maybe a simpler problem. So that's the chain rule visually. Let's do another example, just kind of see this in a longer chain. So suppose, so remember we have a neural network, which is a composition of a bunch of functions. If we want to make a prediction on the image x, then we feed forward the value of x to the graph, to the computational graph. But to compute the derivative, we have to differentiate and backpropagate. So here's a picture. If I want to make prediction on x, then I have to go forward, and that's what we saw in the neural network. But when we differentiate, we have to go backwards. So that's why we call that backpropagate. So here's an example. I want to find the derivative of h with respect to x, which is a kind of a big change, so this might be too complicated. So we're going to break this down into some smaller steps. We first differentiate h in terms of w, because that's the closest and that's the easiest function. So we find dh, dw, so that's this one. Then we use this to compute dh, du. And so how do we do that? Well, we do that by using the chain rule again. So again, the chain rule for this is that dh, du is dh, dw times dw, du. So again, we want to differentiate dh, du. So we first differentiate dh, dw, and you multiply that by dw, du. And so knowing the derivative of this help us find the derivative of the previous variable. And then we do this again. We use the derivative of this variable and help us find the derivative of the previous variable. So we use dh, du to compute dh, dx. Again, this is another application of the chain rule. So this is why this is called backpropagation. We differentiate the last variable in terms of the previous, use that to find the derivative of the last variable in terms of the previous step, and keep going back until we get back to the first variable. Okay, so but here's really what our two-layer neural network looks like. Again, x is all the images. We feed it forward to get the prediction. But after we get the prediction, we can find the cost of that prediction. In other words, we compare the prediction with the actual label. So that's the cost function, or the J function. This is a function of all our parameters. So the output of our network is a function of x, and that's the prediction in terms of x. But the output of the cost function is actually a function of the parameters, these w. So the cost function depends on the parameters, and it's a function of the parameters. In other words, if I change my parameters, I might get different costs. And so what we want to do is we want to find the derivative of the cost function in terms of all the parameters, w1, b1, w2, b2. And so we want to backpropagate to be able to go back and get the derivative of j in terms of these parameters. So again, we want to, even if you don't understand completely the chain rule, the lesson here is that we want to just find derivative of the previous variable, and then just keep going back to get derivatives of the previous variables. So we just want to make sure we understand the intuition behind backpropagation, even if we are not clear on the calculus. So for example, I want to compute dj, the cost function, dw2. So we first compute dj, da2, that's the previous variable, and then use that to compute dj, dz2, that's the one before that. So we use the dj, da2 to find dj, dz2 by using the chain rule. Then we use dj, dz2 to find dj, dw2. And that's what we need to compute and that's the direction that will help us, the direction of w2 that will help us reduce the cost the quickest. But that's only one direction. We need to compute the direction in terms of b2 and b1 and w1. So let's do another one. So let's find the derivative of j with respect to say w1. So again, the further back it is, then the more steps we need to do to backpropagate. So first we have to find dj, da2, and then we use that to find dj, dz2. And then in theory, we can also take a step and go to dj, da1, but it turns out that's actually easier algebraically to go from dj, dz2 to dj, dz1, because those are related, and there's a nice way to write this in terms of this. So we're going to jump and say we're going to use dj, dz2 to find dj, dz1, and then we use dj, dz1 to find dj, d, say w1 or b1. So again, we want to just understand visually this picture so that we can implement the code to backpropagate. So here are the four equations of backpropagation. The first equation, suppose we have an L layer neural network. In other words, we have a neural network with L layer. So we first compute dj, dzl, which is the last layer, and so AL is the prediction, again, the prediction for all the images. This is the output of the network. And Y is the label. We talk about vectorization, so this is all vectorized. And then this O dot represents element-wise multiplication. And sigmoid prime, which is the derivative of sigmoid, is simply sigmoid of x times 1 minus sigmoid of x. So we take this difference of the matrices, divide by m, and then we multiply element-wise by the sigmoid applied to ZL. And then this formula says that if I know dj, dz, I plus 1, that can help me find dj, dz, I. And again, this is part of that backpropagation picture we saw earlier. And this is wi plus 1, so the t is for the transpose. Whereas this is element-wise multiplication, the O dot. The regular dot represents matrix multiplication. Equation 3 says that if I know dj, dzi, then that can help me find dj, dwi. Again, this t is transpose. And finally, if I know dj, dzi, that can help me find dj, dbi. So notice the theme here is that if I know dj, dzi, that can help me find dj, dwi, and bi. And we don't really directly need dj, dzi. We need dj, dwi, and bi because those are the gradients that we need to move and update our parameters, zi is just simply an intermediate step that can help simplify the calculation. So we go through dzi just to get to the wi and bi. And this formula, dj dzi bracket I represent the ith column of dj dzi. And so this essentially says that we add up all the columns of dj dzi, divide by m, and that will give us dj dbi. So there's the four backpropagation formulas. Let's do an example. Well, let's actually show you visually how these formulas relate to the picture that we saw earlier. So again, suppose we have an L layer neural network. We first find djd al, and then use that to find djd zl. So here, this first one is actually very simple. So we can actually do this with just a regular calculus. So remember that the j function, the cost function, is this formula, which is the square of the square distance divided by m. It's the average of all the costs. And so by using the chain rule, we can the chain rule using the power rule says that we can bring down the 2 and subtract 1. If I bring down the 2 will cancel. Subtract 1 will give us this formula. So because the djd al is this, we use the chain rule to get djd zl. And so here's equation 1. So djd zl is djd al times dal dzl. Again, this is exactly the chain rule from Calc 1. And so we take djd al, which is this formula, and element-wise multiply that by sigmoid, because again al is a sigmoid function, so al dzl is sigmoid prime of zl. So this is exactly just the chain rule for sigmoid. So again, this is equation 1, which we saw earlier here. So again, we're going to go through the visual way of seeing these formulas. For equation 2, if I know dj dzi plus 1, that can help me find dj dzi. And this is the formula. We take dj dzi plus 1, element-wise, where you matrix multiply that by the transpose of wi plus 1, then you element-wise multiply that with sigmoid of zi. So again, knowing this help us backpropagate to get the previous derivative. Then equation 3 is similar. If I know dj dzi, then that can help me find dj dwi. And that's simply by matrix multiplying that with the transpose of ai minus 1. And then equation 4 is if I know dj dzi, that can help me find dj dbi, and that's found by adding up the columns of dj dzi and then divided by m. In NumPy, this is the only tricky thing in code is that in NumPy we need to add up the columns to add that up. Remember from lecture 2 when we did NumPy, we want to add up the matrix and we want to collapse the columns, and so that means we want to add it along the axis 1 dimension. So this will collapse all the columns, and this will just keep dims equal true. We'll make sure that our the answer from this sum is 2-dimensional. We want to keep everything 2-dimensional. So you might notice that this is kind of intimidating. These 4 equations are very intimidating. And actually, before we talk about that, let's just do one example of this. Suppose we have a 2-layer neural network, an 8-layer neural network. I want to show you how this is done just algebraically here. So first we differentiate dj dz8 by equation 1. Then from that we can use equation, say, 3. You can use dj dz8 to find dj dw8 by equation 3. We can use dj dz8 to find dj db8 by equation 4. And then equation 2 helps us just take dj dz8 to find dj dz7. And then we repeat this with dj dz7 and help us find dj dw7 and dj db7. We keep going back like that. So these 4 formulas, when you write code, you'll be asked to kind of analyze this to be able to compute these derivatives. So these questions are very intimidating. So you might be afraid of doing machine learning in general, because maybe how do you find these formulas on your own? It turns out that you don't really need to be proficient at advanced calculus to be able to be successful at machine learning. In practice, people usually do machine learning by using deep learning frameworks. For example, Google's TensorFlow will allow you to do all the calculus without having to do them manually like this. So, and the reason why we do it this way is because understanding backpropagation and understanding gradient descent is still important. Even if you're using TensorFlow, we still need to understand gradient descent and backpropagation to be able to properly use the library. So if you're intimidated by these formulas, don't worry too much. When you apply it, when you do this in code, it's actually not too hard. The Jupyter Notebook for this lecture will guide you through the process of writing all this in code. Okay, the last thing we need to talk about is mini-batch gradient descent. So let's look at this again. Remember that to make a step in gradient descent, we need to take our images, our 50,000 images, and feed it forward into the network, and then we backpropagate to find the derivatives, and we update our parameters. But the problem is that we have to take a lot of steps to be able to reduce our cost, and to use all 50,000 images just to make one step of gradient descent is actually very costly and really will slow down our program. And so what we do is that we actually don't take all images when we feed forward. We only take a mini batch. We're going to randomly pick a mini batch of just 10 images. And we feed forward those 10 images and then backpropagate to get one step. So it's just 10 pictures all we need to make one step. And again, because these 50,000 images are evenly divided among the 10 digits, so taking 10 pictures, on average will allow us to have each of those digits. And so this really, the 10 images we pick here is a way to approximate the training data, the entire data set. So it turns out that this is good enough and accurate enough for us. This is a good approximation for the entire data set, and this will also help us quickly run gradient descent. Instead of having to run this with all these images at every step, we only run it on 10 images. So if I use 10 images for each step of gradient descent, that means we can take 5,000 steps if we were to look through this data set once. And so that's called an epoch. That means that we do one complete pass through the entire data set. So that's 10 images each step for 5,000 steps. And then it turns out we're going to have to do this 30 more times. In other words, we have to look at these 50,000 images 30 times. Each time we look at 10 images. And so we'll take a total of 150,000 steps of gradient descent. So here's the pseudocode for this algorithm. So first we're going to randomize W1, W2, B1, B2. Then we're going to do a for loop. This is the outer for loop from 1 to 30 because we're going to look through the data set 30 times. Then inside the loop, we're going to shuffle the training data. So take the 50,000 images, shuffle it. And then we pick the first 10 images. Again, this is shuffle, so this is randomized. We create X and Y, as we saw in the previous lecture, vectorize X and Y, the images and the labels. We feed it forward to get all these intermediate variables. Then we backpropagate to get all the derivatives. Then we update the variables by moving one step in the gradient direction to reduce the cost. So for example, take W1 minus the step size times the derivative or the gradient of W1. And then we repeat this. Take the next 10 images of the training set and do this again. Once we finish an iteration of the entire training set, we do this again 30 more times. So this is a mini batch gradient descent. Congratulations, we've done. We have the final piece that you need to be able to write the complete program that recognizes handwritten digits. So the Jupyter Notebook for this lecture is the last notebook, and it will guide you through writing the entire program. And so I encourage you to work on it first. Look through the lecture, and the notebook will have all the formulas for you. If you get stuck, we will write the entire code in the next lecture. Okay, I hope to see you in the next lecture. And I just want to say one last thing here is that Andrew's Inc. course on deep learning, this is where I get the vectorized backpropagation formulas in this lecture. Michael Nielsen book, where most of the lecture comes from, he actually does it he doesn't do it with vectorization. So I think the code is a little bit trickier to write. And so I think vectorizing it makes the code a little bit easier to write.